Hello, I'm Tatiana Rogers, and I'm currently the lead design engineer for MakerBot. And within the past month, I've done a lot of research trying to figure out the most time and cost-effective ways to bioprint. Today, I'm here to persuade you that switching to cylindrical-based needles and PGA gel is the most efficient ways to bioprint today. And I actually have a formal report titled The Feasibility Study of Cylindrical Needles and PGA in MakerBot's 3D Bioprinters for Lower Production Time and Increased Profits. But today I will be focusing on increased cell viability with PGA and cylindrical needles and CellLink's PGA and cylindrical needles, which are available for purchase and suitable for MakerBot. So I will now go over the current bioprinting situation in MakerBot. We are currently using the extrusion-based technique, which is gelame and the use of tapered needles. But we are wanting to lean towards PGA and cylindrical needles. I will first define cell viability, which is the measure of the thriving cells within a certain sample. And cell viability is measured with three main categories: shear stress, cell 3D scaffolding, and thermal damages. And extrusion-based printing uses high-pressure tapered needles to speed up printing time, but there's a direct negative correlation between cell viability and increased shear stress. And extrusion-based printing often causes the outcome of cells to be extremely damaged or dead, reducing profits. And tapered needles increases the viscosity at the expense of cell viability. By changing the material of the bio ink to PGA, we can actually increase cell viability from 55.52% to 90%. And by changing the needle shape to cylindrical, we can increase profits from 58.7% to 89.1%. Shear stress is an important factor in determining whether or not stem cells will develop and differentiate once implemented in the human body to the correct cell type. And with increased shear stress, cells will often rupture once getting implemented into the human body. And the 3D scaffold will fall apart. And extrusion-based printers at MakerBot currently use gelame, and gelame has a high viscosity rate. And gelame often fails to give an environment suitable for extracellular matrix to form. And using gel-based inks will fail to produce a proper 3D scaffold. And gelame is a fast degrading material. Once put mechanically into the body, the 3D scaffold will fall apart over time. And gelame often lacks the hydrogel links such as collagen that PGA actually has needed to retain the 3D shape. And not using the proper bio ink such as PGA leads to catastrophic profit losses and worsens the reputation of MakerBot. And extrusion-based bioprinting can be one of the longest processes in 3D bioprinting due to constant temperature variability. And temperature variability is due to high pressure, leading to thermal damages within the cells. And thermal damages lead to whole batches of cells being thrown out because they ended up dying. And extrusion printing typically allows for temperature variability to range between 25 to 55 degrees Celsius. And temperatures exceed often 105 degrees Celsius. And this is a dangerous range to be in, since the melting point of gelame is 168 degrees Celsius, but PGA actually has a much higher glass melting point and temperature melting point than gelame. So I will now move on to CellLink's PGAs and cylindrical needles and the cell viability. And PGA produces low amounts of toxicity and is biocompatible with many tissues, able to hold off bacterial infection, and is one of the most cost-effective bio inks on the market. And cylindrical needles are best for increasing cell viability with a lower viscosity because they exhibit lower shear stress. And cell viability increased from 58.7% using a tapered needle to 89.1% using a cylindrical needle. And PGA currently is the bio ink of choice because it is FDA approved. And PGA, when blended with a hydrogel, creates a successful Y lattice shape. And CellLink needles vary in size for the base, but will include the desired optimal cylindrical nail cylindrical needle diameter of 3.17 millimeters, and the needle length MakerBot should be using is 24 millimeters, which CellLink currently has as well. I've included a graph illustrating the cell viability of CellLink as the days go on from 1, 4, and 7 days, using information from Mazzarulli, Valesco, and Esfandiarpour. And CellLink's website currently has an array of bioinks to choose from. The bio ink I recommend is Alligate-based PGL, which is a 10 by 3 milliliter bottle for $999. And this is a really good deal compared to other companies such as Sigma Aldrid for 2,360 per bottle. And they have all CellLink needles will incorporate the 24 millimeter length requirement and the 3.17 millimeter diameter requirement for MakerBot's current bioprinters. So PGA, here's a comparison between PGA, PLA, and PCL. And PGA is the polymer of choice because, like I said previously, has an extremely high melting point and glass transition point. PGA is more acidic and hydrophilic than PLA. And out of all the polymers listed in this chart that I've created, PGA has the largest biocompatibility and mechanical strength. It is FDA approved, but the downside of PGA that I will acknowledge is that it uses glycolic acid, and glycolic acid causes a high friction rate, which could lead to the degradation of cells. But luckily, the company Dexon, which CellLink actually uses, has modified PGA with Polamaxer 188 coating that reduces the friction within the tissues. And in the chart, I am currently comparing the most popular hydrogel links on the market. So when we use tapered needles and gelame, it is called extrusion printing. It is called extrusion printing, like I said before. And using cylindrical needles and PGA, that is called stereolithography. Here's a comparison of the two methods of printing in America today. A kidney transplant would cost around $300,000. The printers at MakerBot are currently $55,000. And the result of printing a kidney can cost around $15 using stereolithography and PGA and cylindrical needles. And that's pretty amazing if I do say so myself. And then selling that $15 kidney that we have created, we can sell it for $20,000 and make exponential profits from that. And this is incredible profit for MakerBot. And per sale, MakerBot could be saving tens of thousands of dollars by switching to PGA and cylindrical based needles. And this will allow MakerBot to save money and time and focus on developing new tissue structures and breakthroughs. And in this PowerPoint presentation, I've currently gone over the benefits of increased cell viability for using cylindrical needles in PGA and the benefits of CellLink's PGA and cylindrical needles. Like I said before, the cost of using these is low and the cell viability is typically ranges at around 85%. The print speed is a lot faster than our previous speed, which is the extrusion based printing, and the resolution that we can print from these cells is pretty high, and the quality of the lattice is good as well as it was previously with extrusion based printing. But there's no limit to the viscosities while using PGA and cylindrical needles because the pressure and shear stress decreases significantly. So thank you so much for listening today. And I really hope that I can get to see, I'm excited to see PGA and cylindrical needles be implemented within MakerBot. And I'm excited to see the future of the company as MakerBot continues to lead America and many forms of 3D bioprinting, and will continue to lead with new inventions that we will make with 3D bioprinting for tissues using our new stereolithography methods.